Hi everyone, this is Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the non-ferrous alloys. So in the previous session we have discussed about the how the characterizations of the steels are being formed depending upon the iron-carbon phase diagram. And from this iron-carbon phase diagram, we have classified different types of steels like the depending upon the composition, we have classified different types of steels, as well as the classifications of different irons also we have classified based upon the iron carbon diagram. So all these classifications are depending upon the composition rate of the carbon content present in the material or the alloy. So like that we have classified different types of steels as well as the cast irons. Now in this session we are discussing about the non-ferrous alloys. The ferrous alloys also we have discussed in the previous session. So ferrous alloys are nothing but the alloys which are having the major constituent as iron. Okay, so the materials which are having the major constituents as an iron are called the ferrous materials. Now coming to the non-ferrous alloys, so in this there is a no presence of iron, then the type of alloys are called as non-ferrous alloys. So non-ferrous alloys represents with 0% or there is no composition rate of the carbon content present or the iron content present, then that type of alloys are called the non-ferrous alloys. Now if you see the definition here, the non-ferrous alloys all that are not iron based. Okay, so where there is no content of iron, then those types of materials or those types of alloys are called the non-ferrous. And steels and other ferrous alloys are consumed in exceedingly large quantities because they have such wide range of the mechanical properties. So because of the large availability of these mechanical properties, that's why these steels and other alloys have been consumed more because of the availability. And these may be fabricated with relatively ease and are economically to produce. So these are some of the criteria or some of the importance. That's why we are going with these types of steels and other type of ferrous alloys, because of the good mechanical properties as well as the production rate is very good when compared to other type of alloys. What are the ferrous alloys are there, what we are using or what we are consuming very high rate when compared to the non-ferrous. So these will also have some drawbacks. So what are the drawbacks? If you check once, see, first one is the relatively high density. So because of high density, okay, so these are having some limitations, restrictions or some limitations by using these steels as well as the alloys. So first one is the high density. Because of the density, what is happening, the weight is becoming very high. And second one is comparatively low electric conductivity. So because of the low electrical conductivity, so these have made drawbacks in some applications. And the third one is inherent susceptibility to corrosion to some common environmental conditions. So whatever the steels are there, so these will easily get to corrosion. Okay, so because of the corrosion, what is happening, the life cycle of the metal will get down. So all these things are some of the limitations where the ferrous alloys or the steels or the alloys have been used. So what are those? First one is the high density. So because of the high density, the weight of the metal will increase. The second one is the low electrical conductivity. So because of the low electrical conductivity, so it is not applied to some of the applications where the electrical conductivity rate has to be increased. And coming to the third limitation is that inherent susceptibility of the corrosion. So the metal will get easily corrosed. So because of the easily corrosion to different climatic conditions, so the life span of the metal will get reduced. So all these are some of the limitations while using the ferrous and type of alloys. So that's why these ferrous alloys are replaced with the non-ferrous alloys in which there is no presence of the iron content or iron base. So those types of materials are called as non-ferrous materials. So that's why for many applications it is advantageous or even necessary to use other alloys that have more suitable property combinations. So because of the replacement of these ferrous alloys, what we are trying to do, we're trying to get some more good materials. With these materials, the same properties which can be available in the ferrous materials, the same properties can be achieved in this non-ferrous alloys also. So that's why alloy systems are classified either according to the based metal or according to the specific characteristics that group of alloys are shared. So here we are classifying each type of alloy based upon the characteristics. Characteristics again is nothing but the physical, mechanical or chemical properties. So based upon these properties or presence of the iron content, so we are classifying these materials. So there are large number of non-ferrous materials covering every metal and alloy that does not contain iron. So we have a lot of non-ferrous materials which does not contain iron. So everybody thinks that the material which is having iron base, so these only have the good mechanical properties and these have the many regular applications what we are doing or what we are using in the present life. But still if there is no content of the iron, we have a lot of materials. So these materials are applied or applicable, can be applied in many applications. So what are those types of non-ferrous materials means? The non-ferrous material include the aluminium, copper, lead, nickel, tin, titanium and zinc, as well as copper alloys like bronze and brass. So these are some of the materials which are having a non-iron base, and these can be used in many applications. Okay, so these are some of the non-ferrous materials. So other rare or precious non-ferrous materials includes the gold, the silver, platinum, cobalt, mercury, tungsten, beryllium, bismuth, beryllium, cadmium, indium, gallium, germanium, lithium, selenium, titanium, vanadium and zirconium. So these are some of the rare metals in which again there is no content of iron present. So these are a lot of materials are available with there is a 0% of iron content. So these materials are being used in many applications without the iron based content. So these are called as a non-ferrous alloys. So generally the non-ferrous metals are usually obtained in from where we are getting from minerals like carbonates, silicates and sulfates. So from these are the base materials from which we are getting the non-ferrous materials. So before being refined through electrolysis process, so we are getting all these types of non-ferrous materials from the carbonates, silicates as well as the sulfates. Okay, so from these three groups we are getting the non-ferrous alloys. And the difference between the ferrous and non-ferrous metals is that the ferrous metal contain iron, of course. So wherever the iron content is present, that comes under the category of the ferrous type of alloys. So the ferrous metals such as cast iron, carbon steel have high carbon content, which generally makes the vulnerable to rust when exposed to moisture. So when compared to the non-ferrous materials, ferrous metal will get easily corrosion. So when compared to the non-ferrous material, these ferrous material will get easily corrosive when exposed to different climatic conditions. Why? Because the content, the percentage of carbon content is very high in these ferrous materials. That's why the cast irons or the what are the carbon steels are there. So these are having the high percentage of carbon content. So because of the high percentage of carbon content in this, these ferrous materials are when exposed to different climatic conditions. What is happening here? There is a formation of a rust. So because of the formation of rust, what is happening? There will be some failures in the material during the working process. Okay, so that's why we can replace these ferrous materials instead of the ferrous metal with the non-ferrous materials. So however, this is not the case for wrought iron, which resists rust due to its impurity, and the stainless steel, which is protected from the corrosion by the pressure of chromium. So apart from these ferrous material like cast iron or the carbon steel, the wrought iron as well as the stainless steel, these are corrosion resistance materials. Okay, when exposed to different climatic conditions, these are corrosive resistant materials. So because of the presence of the chromium inside the wrought iron as well as the stainless steel. So it is happening. It can avoid the rust formation or the scale formation around the material. So apart from these two materials, but other the cast iron as well as the carbon steel will have the high effect of the corrosion to the material. Now, if you see one by one, what are the different classifications of the non-ferrous elements? So, first one is the copper and its alloys. So, copper comes under the category of the non-ferrous, and if you add some alloys to that copper, what is happening? We can enhance the properties of the copper material. If you have only single material, it has a normal properties, but one more alloy if you add to the base material. Okay, so we can't add many type of alloys here. Only the copper can get some good properties when you add some alloying elements. So what are those adding alloying elements to the copper? We'll see. So copper here is the base materials. So for the base material you can add some alloying element to enhance the properties. Okay, so copper, that's why copper and its alloys. So copper and copper based alloys processing is a desirable combination of physical properties, have been utilized in quite a variety of applications since ancient times. So unalloyed copper is so soft and ductile that is difficult to machine. So also has an almost ultimated capacity to be cold worked also. So if you have a pure copper, so it is very difficult to do the machining process. That's why we are adding some alloying to this material so that we can do easily machinable. And also it is highly resistant to corrosion in diverse environments. So maybe it can be a minus degree centigrades or a very high temperature or different climatic environmental conditions. That's why in diverse environmental conditions also the copper as well as its alloys can resistance to the corrosion. And like ambient temperature, sea waters, some industrial chemicals. So when the copper is exposed to these types of environmental conditions, that is the diverse environmental conditions like sea water or industrial waste or industrial chemicals what we are releasing, as well as the ambient atmospheric temperatures. So all this it can withstand, you can resist to corrosion. That's why any material or any system which is working under these climatic conditions, then you can go easily with the copper and its alloys so that you can avoid all the rust formation or the scale formation around the material. So the mechanical and the corrosion properties of the copper may be improved by alloying. So if you want to increase the mechanical properties, what you can do, you can add some of the alloys to the copper so that these properties can be improved. So generally how we are adding an alloy to the system means we are doing some heat treatment process, then we are adding some alloying element. But in case of the copper, we can't do the heat treatment process, we can do by the cold working process only. So with the help of the cold working process, you can add some alloying element into that so that you can improve the mechanical properties and you can resist from the corrosion. Subsequently, the cold working process or the solid solution alloying must be utilized to improve these mechanical properties. So because it is not done with the hot working process, the copper material, so different materials will have again different working process. So here the copper will have the alloying when there is a cold working process only, without the rather than the hot working process. So that's why the cold working or the solid solution alloying must be utilized to improve these mechanical properties when it comes for the case of a copper. So what is the most common copper alloy? Means copper we are adding to the copper means brass. So when you add brass, and also you can some more if you add, for which zinc is a substitutional impurity, so that we can predominantly increase the mechanical properties of the element. So initially the copper will have normal type of properties. Now if you want to increase the mechanical properties, so what we can do means we can add the common most alloying element for the copper is the brass. And of course if we add some more zinc to that brass also, you can predominantly increase the mechanical properties of the copper metal. That's why it's called the copper and its alloys. So copper is the base material. For this base material we are adding some alloys to improve the mechanical properties, so that for this copper the brass as well as the zinc are the impurity alloying elements for enhancing the mechanical properties. Now, if you see the chart, you can easily find out what are the different types of compositions you have for the copper, and based upon the compositions, what are the mechanical properties, and based upon the mechanical properties, what are the applications. So, as we discussed in the previous classes, so if you want to decide a material, you have to know first of all what are the characteristics of that materials. So once if you know the characteristics of the material, the characteristics include the properties, the compositions, everything. So once if you know the characteristics of the material, then it is very easy for us to select the material for the required applications. So in the same way, what type of copper and what type of alloying element can be utilized for our applications, we'll see based upon the mechanical properties. Now, here the copper is your base material, so we are not repeating the copper, so we are just repeating that alloying element. So we are adding the alloying element for the copper. So here if you see the alloy name, first one refers to the alloying name. So electrolytic pitch, the next one is beryllium copper, cartridge brass, phosphor bronze, copper nickel, lead yellow brass, tin, aluminum. So all these are some of the alloying element which we are giving to the base material, that is the copper. So based upon that combination, again you are giving some specification to that type of material. So what type of material based upon the composition we are adding. So what is the composition of each element here? What is the percentage of composition we are adding? So based upon the composition to the alloying element, at what condition, whether we are doing it heat treatment process or cold temperature, all these are the conditions where we are doing the alloying element. Now, after adding those alloying element, what is the strength we are getting? So here the tensile strength, next is the yield strength, next is the ductility. So these are some of the properties of that copper which is having some alloying elements. So based upon those properties, where these materials can be utilized in the application. So first one, if you see, if you want to go with the electrical wire, rivet, screening gaskets, then you have to go with these type of materials. Similarly, if you want to go with the clutches, disc, diaphragm, fuse, clips, then you have to go with the phosphorus type of alloying element to the copper. Similarly, for the furniture of hardware, radiator, flying fittings, light fixtures, battery clamps, then you have to go with the lead, yellow or brass, and these are some of the compositions to the base material. So like that, depending upon the composition rate, we are getting the classifications of the material. So based upon the classifications, we are getting the mechanical properties. Again, from the mechanical properties, we are giving the application. So this is how you will use that non-ferrous material like a copper to the application based upon the typical conditions of the type of heat treatment process or cold working process we are doing to add some alloys to the base material, that is the copper. And coming to the next category of the ferrous, so first one we have seen the copper, the second one is the aluminum and its alloys. Again, in the same process, aluminum is the base material. For this base material, we are adding some more alloying element. So in the previous case, we have added the brass and zinc to improve the properties of the copper. Now in this case also, the same may not be suitable. So we have to do some research process in order to find out what type of alloying element is suitable for the base material, so it can enhance the mechanical properties. So in this case also, we are using aluminum as the base material, and we'll see what are the alloying element for these aluminum to enhance or to predominate the mechanical properties. So aluminum generally is a little low density type of material. So what is the density range here? So low density around 2.7 gram per centimeter cube to 7.9 gram per centimeter cube, and high electrical and thermal conductivity and the resistance to corrosion in some of environmental conditions, including the ambient atmospheric temperature. So many of these alloys are easily formed by virtue of high ductility, and this is evidenced by thin aluminum foil sheets into which relatively pure metal can be brought. So what is happening here? Aluminum and its alloys are very low density. You have very less density. That's why the weight of the metal is very less when you compare with the other type of high density material like ferrous materials. Now these are very high electrical and thermal conductivities, and resistance to the corrosion also at different climatic conditions like ambient temperature. And also these are found by virtue of high ductility. So these are having very very ductile nature, the aluminums. So why it is ductile means it can machine in any type of things, it can bend in any different types of forms. So because of the high ductility, the simple example means you can easily roll aluminum foils, or what are the aluminum foils we are getting, because of the high ductility nature it can be rolled into a thin form of sheets. Okay, so that is the examples of the high ductile nature for this aluminum. And the mechanical strength of aluminum can be enhanced by cold working and by alloying, however both process by diminishing resistance to corrosion. So here also the aluminum also it is taking as a cold working process. Under cold working process only we can enhance the mechanical properties of these aluminum, and in order to improve the mechanical properties, which improves the corrosion to resistance also. So what is the principal alloying element for the aluminum, which includes the copper, magnesium, silicon, manganese and zinc. So these are the some common alloying element. If you add these alloying element to the aluminum, we can easily enhance the mechanical properties of the metal. So what are those? So these are the copper, magnesium, silica, manganese and zinc. So these are some of the alloying elements which useful for the aluminum to increase the properties. And also non-heatable alloys consists of a single phase for which the increase in strength can be achieved by the solid solution strengthening. So like this you have different types of working process, whether it is under cold working process or hot working process, depending upon the type of metal we are using. So both the copper as well as the aluminum are under the cold working process only, we can enhance the properties. But aluminum has some annealed process also, we can slightly increase the temperature and we can do the any alloying elements also. But in the case of aluminum it is completely of cold working, under cold working process only. So again if you see the chart of the properties as well as the composition and types of applications for the aluminum alloys, again based upon the composition rate or based upon the alloying element we are adding, these are some of the classifications of the aluminum: 1100, 3003, 5052, 2024, 6061. So these are some of the examples of the aluminum alloys, and based upon the composition rate. So here 0.12 of the copper, manganese, zinc 2.5 of manganese, chromium 0.25. So these are the composition rate what we are using. So how we are adding, based upon the temperature conditions, at what temperatures you are adding these alloying elements. So based upon the alloying elements, so initially some may have less values of tensile, so it is increasing up to 90. So 110, 230, 470 megapascals, 240 megapascals. So these are the values of the tensile strength. Suppose in the case of, if you see the yield strength, 35 for the 1100 aluminum, 40 for 3003, 195 for 5052, 325 megapascals for 2024, and 6061 we have 145 megapascals of yield strength. And these are the ductile nature of the material. So 35 to 45, 30 to 40, 12 to 18. Like, so there is a different types of elongation percentage we have the ductile nature. And if you see the example, suppose if I want 5052, so where these can be applied, so based upon the mechanical properties I will decide these 5052 type of metal can be utilized in the aircraft fuel and line, oil line or fuel tanks, appliances, rivets and wires. So these types of things wherever are there, we can go with the 5052 of aluminum alloys. Again, if you want for the food or chemical handling storage equipments, then you have to go with the 1100 type of material. And again, for the cooking utensils or pressure vessels, then you have to go with the 303. So what are the cooking utensils we are using in the day-to-day life are made with the 3003 type of aluminum alloy. And again, you have another type of alloying elements: 7075, 2950, 350.6, 2029, 890. So these are the different other types of aluminum alloys when it is under heat treatment process with some another type of silica or copper, magnesium, lithium percentage. So aircraft cryogenics, you can go with these types of 2029. And if you want to go with the aircraft structural parts, then you have to go with the 7075. So all these are interrelated. So based upon the type of variations of the compositions we are giving to the base element, that is the aluminum, then we are changing the mechanical properties. So based upon these properties, again the applications are being varied. So other type of the non-ferrous metal is the titanium and its alloys. So titanium is the base metal again in this case. So this is the new type of engineering material which has an extraordinarily combination of properties. So when you compare with the aluminum and the copper, so this titanium is a newly developed engineering material which is having extraordinary combinations of the properties. So the pure metal has a relatively low density of 4.5 gram per centimeter cube and high melting point of 1668 degrees centigrade. So this is a good thing what we can see, which is having a low density of 4.5 gram per centimeter cube and which is having a high melting point of 1660. So at high temperature conditions also we can use with these titanium type of materials so that it can withstand up to the temperatures. So elastic modulus, which is having a 107 gigapascals, and these titanium alloys are extremely strong at room temperature, and the tensile strength will be around 1400 megapascals, which are attainable, so yielding remarkable specific strength. And furthermore, if you alloy some of the things to the titanium, then you can easily increase the ductile nature as well as the it is very easy for us to do the machining process. So these are some of the good qualities of the titanium material when you compare with the aluminum as well as the copper, because it is having a high melting point around 1600 degrees centigrade, and also it is having a good elastic modulus of 107 gigapascals, which is having a low density of 4.5 gram per centimeter cube. So unalloyed type of metal, that is the, if you are not adding any type of things to the titanium, which is having a closely packed crystal structure, hexagonal closely packed HCC type of crystal structure. But once you add some alloying element, it will change its crystal structure. So change of crystal structures we have seen in the previous sessions of the phase diagram. So in the same case, when you does not add any alloy to the base metal of the titanium, then it has a hexagonal closely packed type of crystal structure, which is having at alpha phase at room temperature. So at 883 degrees centigrade, this HCP material transformed to BCC, that is the body centered cubic structure. So they at the room temperature, it is having a titanium at room temperature has a hexagonal closely packed type of crystal structure. At 1883 degrees centigrade, this HCP is converting into BCC crystal type of structure. So this transformation of temperature is strongly influenced by the presence of alloying element. So how we are getting this transformation of the titanium to the from HCP to BCC means because of the alloying element. So the major limitation to titanium, it is chemical reactivity with other materials at elevated temperatures. So when you do the alloying element at elevated temperatures, so this is the transformation what we are achieving. So this property has a necessary development of the non-conventional refining, melting and casting techniques. Consequently, the titanium alloys are quite expensive. So because of the any changes if you are trying to do, so this has to be done at a high temperatures or high elevated temperatures. So because of these process, these are very expensive when you compare with the aluminum as well as the copper. In spite of this high temperature reactivity, the corrosion resistance of the titanium alloys at normal temperature are unusually very high, and they are virtually immune to air at marine and ferrite industrial environmental conditions. So in the same way, if you see the for the titanium, what are the difficult alloying elements here? Commercially pure titanium, if you see, it is which is unalloyed, which is having tensile of 240 megapascals and 170 yield strength, and ductile nature is 24. So where can you use these types of commercially pure titanium means in this case of jet engine shrouds, cases, airframe skin, corrosion resistance equipment for marine or chemical processing industries. So these are some of the categories where the pure titanium can be used. Now slowly if you add some of the other things to the titanium like tin or molybdenum, okay, like these types of compositions if you're adding to this, so what is happening slowly, it is converting, it's increasing the properties of the tensile strength, yield strength as well as the ductility nature. So because of those increasing in the properties where the applications are being changed to best combination of high strength and toughness, of any commercially titanium alloys used for applications of requiring uniform of tensile properties in surface and center location. So these are some of the applications of pure titanium as well as the alloying titanium. Okay, so in this session we have discussed about the non-ferrous alloys which are not of iron base. So the elements which are of uh, iron based are called ferrous, but in this session we have completely discussed about the non-ferrous elements which are having a 0% of carbon content, and the different classifications of non-ferrous metals we have discussed in this. And based upon the alloying element, what are the changes in the properties we have identified? Based upon the properties, how the classifications of the metals have been done, and based upon these, what are the typical applications we can achieve when we do the alloying element, we have discussed in this session. So these are some of the references books where you can identify or where you can get the information about the non-ferrous metals. So first one is the Introduction to Physical Metallurgy by Sidney Hefner. The second one is Essential of Metal Science Engineering by Ronald. The third one is Metal Science and Metallurgy by Kodigiri, and the fourth one is Metal Science Engineering by William Caston. So thank you for the session.
Like, share and subscribe. Hit the bell icon for more updates.